So today we're going to actually go back to that lesson 6.3, which maybe you recall had to do with infinity. I'm just going to finish up a couple concepts that actually still fit into that lesson. Repeated decimals and limits. Now I'll show you these screens again, but I just want to see these will be our two ideas. So what's up with repeated decimals, expressing them as fractions? Well, it appears that we can use an infinite series. Now, I hope those words aren't just kind of getting jumbled in your mind. If we say infinite series, we're talking about adding an infinite amount of numbers, and there's a formula for that, right? There's a formula for an infinite series. It's that kind of that simplest formula. So I wonder how that formula can be used to express this repeated decimal as a fraction. Well, it has to do with first realizing that there is a sequence represented by these decimals, by 370 thousandths, literally 370 thousandths. Then 370, not thousandths, but 100,000, also known as a million, 370 million. How about the last one? Yeah, you got it. I'm just going to add 3 more zeros, and I believe that number is a billion. But it's not just these 3 numbers, it's the sum of these 3 numbers. You see, when you add these fractions, you essentially create this decimal. And of course, we know that this pattern would go on and on, ... So how do we find the sum? How do we find the sum of an infinite amount of numbers that follow this pattern? Yeah, we're going to use this sum formula, this infinite sum formula. All we need is the first term. We got it. It's right here. And we need the R value. And that R value would be what number we're multiplying by. Yeah, each time we're multiplying by another thousandth. Now, I'd be remiss if I didn't say that, and this is all true because this problem is geometric in the first place, right? This problem is geometric. So we're going to use the infinite series formula. We're going to take the first term, and we're going to divide it by 1 minus that common ratio. Now, before you get your calculator out, part of this lesson is to realize that we can simplify this clunky fraction. So, first of all, the denominator, 1 minus 1,000th, is the same as 1,000 thousandths minus 1, right? 999 thousandths. Next, we're dividing by 999. That's the same as multiplying by the reciprocal, right? So I can take 370, but now I can multiply by the reciprocal. So the problem becomes a multiplication problem, which conveniently allow those thousandths to cancel. And I think I have a fraction. 370 over 999. Now, 370 over 999 just so happens to reduce by 37s. If you reduce it by 37s, you get 10 over 27. But it's more the process that we're interested in here. And again, the process, if you work backwards, is to create an infinite series formula. That infinite series formula requires the first term, and it requires that common ratio. And I got that first term and that common ratio by basically thinking of this repeated decimal as the sum of a sequence of numbers that themselves were each multiplied by 1 over 1,000. Ready to try one? Well, maybe. I gave you a problem here that it's conveniently a little bit different, but not too much different for us to understand how we can turn this thing into a sequence. Let me help you get started. We got 1.83. To be honest, I'm not sure if it really matters where I put the repeater. I'm going to leave it the way that I gave it to you here, but yes, it starts repeating when we get to the 3. Which means that so far, this problem, or at least initially, this problem can be described as 1 plus, I'm going to change that to a fraction, 1 plus 8 tenths plus 3 hundredths plus 3 thousandths. Now, do you see that we're getting to the part of the problem that's starting to repeat? 3 ten-thousandths, ... So it's this part of the problem that appears to have the pattern that appears to be geometric. Yes, it's geometric with an R value of 1 over 10. So what I want to challenge you to do is see if you can, with just the numbers in the blue part, just the numbers that are geometric, can you describe that sum? Can you describe that as an infinite series? Don't worry about these numbers out here. They're not part of the formula right now. So can you write an infinite series for 3 over 100 plus 3 over 1,000 plus 3 over 10,000 ... Go ahead, give it a try. You're just using the first term, 3 over 100, divided by 1 minus that common ratio. Just like we did in the other problem, 1 minus 1 over 10. 1 minus 1 over 10 is 10 over 10 minus 1 over 10. That's going to be 9 tenths. But dividing by 9 tenths, that's the same as multiplying by the reciprocal. So we're going to multiply by 10 over 9. Get a little cancellation going here. Get a little cancellation going here. And it looks like we end up with 1 over 30. We get 1 over 30. Now, what's 1 over 30? Well, that's the value. That's the value of the sum of all these repeated numbers. But I still have a 1 plus 8 over 10. Well, just take that 1 plus 8 over 10 and add it with your 1 over 30. You see, ultimately, when you add these numbers together, you're going to be creating 1.833. But we need to write this as a fraction. We need to write all of this as a fraction. So a little more adding to do. We just need a common denominator. Common denominator of 30 multiplied by 3. Common denominator of 30. So we end up with 30 plus 24 plus 1. I think that's 55. 55 over 30. And that is the same as 8.3 repeating. We just use the idea of an infinite geometric series along with some just regular non-repeating numbers to come up with our 55 over 30. Now, I think you can reduce that. Yes, you can reduce that by 5s. So that's nice to know, but I'm more concerned about the process of getting there. We're going to switch gears now, and we're going to talk about what's known as a limit. Okay, now don't worry, this is a new idea. Actually, it's one of the first ideas you'll study in calculus next year. So you might say this is a little bit of a preview, but it certainly fits into the idea of sequences and patterns, and particularly infinity, which is still part of this lesson. So what's a limit? Well, in simple terms, it's an intended y value. It's an intended y value of a function. And don't think of a limit as necessarily like a maximum, as if you've reached your limit. That's not actually at all what it is. It's actually just an intended value of a function. Now you might say, well, what do you mean an intended value? Well, you'll see in a sense, it's kind of the value that the function is approaching, but never reaches. And that's why we say it's an intended value. Now what I'm creating here is, well, it's a limit statement. And if you'll allow me, I'll explain that, first of all, the word limit is abbreviated, LIM. Underneath it, it describes where the x value is going. So we would say the limit as x approaches infinity. And then x plus 1 over x squared is your function. So what's really happening here is we're kind of asking, what is going to be the value or the y value of this function? What's going to be the intended value as x gets really big? Well, I think we could find the value of this function when x equals like 1. In fact, it's pretty easy to find out what happens when x equals 1. You could just plug in 1. It's just going to be 2 over 1. And I bet we could find out what happens when x equals 2. We could just plug in 2, which looks like it'd be 3 over 4. But this is going to take a while. It's going to take a while to make x go to infinity. So let's pull out a little friend here. Let's pull out the graphing calculator. Now, I'm using the graphing calculator in perhaps a slightly different way, basically to help us quickly see what happens when x keeps getting bigger and bigger. So I'm typing the equation into the y equals screen, but I'm not going to graph it. Instead, I'm going to use the table feature. Now, the table feature is ultimately right here above graph. But before I just hit the table button, I need to set up the table. Now, when I set up the table, I can tell it where I want to start. And we're going to start at 0, just because that's a good number to start with for our pattern. I'm going to make my x's change by 50. That just kind of gets us there a little faster. So instead of plugging in 1, 2, 3, we're actually going to plug in 50, 100, 150. So it's a little setup of my table. Finally, we will hit the table button, and we start to generate some y values. Now, it just so happens that when you plug in 0, you don't get a value, you don't get a real value. But look what happens when you plug in 50, 100, 150. Look what kind of values we're getting over here. They look awfully small. Let's plug in some more numbers. 350, 400, 500. Look at these values. Okay, if you're just saying, well, they're kind of decimals. Well, yeah, but they're decimals that are getting closer and closer to 0. Now, we never actually get to 0, but we start to get to the point that the calculator kind of says, all right, I can't write 0.0000 any longer, so I'm going to tell you that the answer, or that the value, is like scientifically small. Now, once again, I never actually get to 0, but it's like I keep getting closer to 0. And that's because the limit of this function, the intended value of this function, is approaching 0 as x gets really big. Now, there's something to say about x getting really big, especially when you have a function of this nature that is a fraction. You see, when you look at the numerator of a fraction, if x is going to get really big, I'm going to have a really big number plus 1. Well, it doesn't really matter about the plus 1 because I have this really big number. And if you look at the denominator of this fraction, I'm going to have a really big number that gets squared. What I'm trying to say here is that the highest powers in this function, that is the highest power in the numerator, just x to the first power, or x. And the highest power in the denominator, which really is just the denominator, they're going to rule. They're going to have the most power in this equation. They're going to basically dictate what happens when x goes to infinity. Again, the number 1, that's not going to change this problem that much. What's going to change this problem is the highest powers of the numerator and denominator. Now, if I take the highest powers, I just so conveniently am able to simplify this fraction. I'm able to simplify this fraction to really just be 1 over x. And if you think about it, 1 over x is like saying 1 divided by x. 1 divided by infinity. Now, there is no infinity button on the calculator, but 1 divided by infinity, that concept, yes, is getting closer and closer to 0. So we have the limit of the function 2 ways. We have the limit of the function by looking at a pattern on a calculator, or we can take the highest powers of the numerator and denominator and ultimately come up with a conclusion that we're going to be dividing by a super big number that gets closer to 0. I wonder if we can use this this numerator-denominator method exclusively. Well, we can. We can, because it's the limit as x approaches infinity. And when you talk about infinity, you're talking about big numbers. And when you're talking about big numbers, the only thing that's going to affect the the overall result of this problem is going to be the highest powers. You see, what I can really do is just kind of grab the highest power in the numerator and the highest power in the denominator and say that those two parts of this fraction are ultimately going to control what happens as you get really big. You say, what about this 6x? Well, the truth is, it's not big enough. Not big enough compared to 4x cubed. So I can take 4x cubed over 2x cubed. I can create this this revised looking fraction. If I do some math, it looks like that the 4's and 2 will reduce. If I do some math, it looks like that the x's will cancel. Wait a minute, I just get 2 over 1, or just 2. Does that mean that this function is going to get closer and closer to 2 as x goes to infinity? Well, yes, it does. It doesn't mean it's going to ever get to 2, but it does mean it's intending to get to 2. And we were able to very quickly come up with this limit by just thinking about the highest powers. Let's try it one more time. Again, when you have a limit approaching infinity, that is as x approaches infinity, you're able to just take the highest powers of the numerator and denominator. I know it almost seems too easy, but the reason you can do that is because the highest powers are going to have the most power, no pun intended, or maybe pun was intended. They're going to have the most power when it comes to the value of this answer. This little plus x is not going to affect the final answer, not when you go to infinity. Now, if you do a little bit of simplifying here, you end up with x squared. X squared. Now, x squared is like the simplified version of this equation. We still have to think about what happens if x gets really big, because that's what it means for x to go to infinity. Now, I can't really plug in infinity. I mean, I can write it, but mathematically, I can't do infinity squared. But I can think, what would that represent? What would be the intended value of something like a big number being squared and then a bigger number being squared? Yeah, you're right. It's not going to get to any intended value. It's going to itself just keep getting bigger and bigger. So the actual limit, the actual answer, is infinity. Limits involving infinity. Well, you can use this power method. That is the highest power of the numerator and denominator. It gets you a simplified fraction which then can help you to determine your final answer as x goes to infinity. Now you should be good to go to think about and try the remaining parts of that digital homework helper. I believe it's like F through G, or maybe there's a couple other questions there, but you're going to start with letter F, and then you'll be able to finish that part up.